Hello everyone, myself Parag Borania, roll number 17BPE013. So concerning to the assignment 2 that was given by our faculty mentor Dr. Pawan Gupta, I would like to thank him for this wonderful opportunity. Our topic of discussion will be diffusivity equation for the real gas flow, its derivation and solution. So I hope you would like it. So let us begin with the presentation.
Let's start with the presentation that is on diffusivity equation of real gas flow, its derivation and solution. So this will be our presentation outline. We will look it upon the diffusivity equation for slightly compressible fluid that we have already studied in the earlier classes. We will look upon their assumptions and limitations, and we will also look that are those assumptions applicable for real gases or not. We will derive the diffusivity equation for real gases. We will also look upon the methods of solution for the differential equation solution. There are three methods, that is solution method, squared method and pressure method. So we will look in a large proportion for the exact solution method, and we will just put some light and see the solutions of the other two methods, and at the end we will compare all the three methods and under which condition we should apply the three of the methods. So let us begin. So this equation we are already aware about, that is diffusivity equation for slightly compressible fluid, that is derived by applying the basic principle of mass conservation, that is mass flow rate in minus mass flow rate out is equal to rate of change of mass in the volume element. So this is the final equation that we are arriving after assuming many of the things in between, and this is in the field units, and here are the depicted terms that we have taken into consideration. So these are some of the assumptions and limitations that we considered while deriving that equation, that are homogeneous and isotropic porous medium, uniform thickness, single phase flow, laminar flow, and the final two assumptions are quite opposite for the case of the gases that are not followed by the gases, that is rock and fluid properties independent of pressure and constant compressibility, that are not in case of the gases, that will be opposite. So as I have told, we have taken some of the assumptions in between, that where viscosity was independent of pressure, so we neglected that term while deriving the diffusivity equation. We also neglected the del P by del R square term as well, and we considered that compressibility was very low and less than 1. So now what is the difference in assumptions that we are considering for the real gases? That the two properties, that are gas viscosity and density, will vary significantly with pressure, and therefore those last two assumptions will not be followed by the real gases. That is, viscosity and density will change as the pressure will change for the gases, that is for compressible fluids. So now let us move for the derivation of diffusivity equation. So we will consider two of the basic gas equations that are required for the derivation. Rest of the things are similar to that of the liquid, but we have to incorporate these two equations, that is real density equation, that is obtained by the equation of state, that we already know, that is PV is equal to nRT. On solving and incorporating density term, we will arrive at this equation A, and we also know the gas compressibility equation. So now we will incorporate this equation A and B in the differential form of the equation, that is for the liquid. We know the final differential equation for the flow of any fluid in porous media, so we will just incorporate these two equations in that differential equation for the liquid, and at the end we will arrive at this diffusivity equation number 3. So you can see that there are viscosity and compressibility factor terms as well. So this is not the final equation for the real gases, this is the non-linear form of the equation. We will look upon how to solve this equation and what is the final results in the further slides. So the term which we are incorporating here is the real gas potential. Now what is real gas potential? Real gas potential is the capability of a real gas to wield the pressure, and it is defined as mp is equal to integration from 0 to p by mu z dp. That you can see that gas potential is inversely proportional to compressibility factor and mu. So we can differentiate the above equation and we can arrive at equation number 5, and as we have told that the things are dependent on pressure, that is explicit. The chain rule will also be applied, and the pressure which is present in MP is also required to be differentiated. So we are differentiating this equation number 5 with respect to position R and time t. So equation 6a, moving ahead, these are the equation number 7a and 7b are obtained by placing the equation number in equation number 5. So this is the final equation that we will arrive, that is the final radial diffusivity equation for the compressible fluid. The difference only you can see that the pressure terms are replaced by these real gas potential term, that is MP. The rest of the things are same as for the liquid. So now there are the three methods of solution as we have mentioned in the presentation outline. There are MP solution method, pressure squared method, pressure method. So we will look upon in the vast for the exact solution method, and we will just see the results of other two methods and we will compare it at the end. So the first solution method, that is MP solution method, also known as Al-Husseini-Ramey-Crawford solution technique. So there were other reservoir engineers who tried to solve this equation for the real gases, that were Russell and Goodrich. What the good thing that they have done is they removed the viscosity is dependence on pressure, so that made the problem easier for Al-Husseini, Ramey and Crawford. So the problem was initially partially solved, and the term phi mu c by k is not constant for the gases, as we all know that mu and c will be dependent on pressure. So equation 8 is the non-linear form of the diffusivity equation. This is equation number 8. So further going for the solution, we will incorporate the compressibility term, as we all know that C is equal to minus 1 by V, del V by del P. We will go for the flow rate Q. So V can be defined as pi RE square H phi C, that is the effective drainage of a radial volume element, where RE is the effective radius. So we will place this equation number D in the del MP by del T term. So further moving ahead, substituting equation 9 in equation number 8 in the differential form of the flow for the porous media, and we will also use another real gas equation of state, that is the conditions which we are getting are at the surface reservoir conditions. So we have to place it by the surface conditions. So this is the generally the comparison of the reservoir condition and the surface condition by the equation of state, and on further simplification we will arrive at this final equation that you are seeing on your screen, that is equation number 12, that includes the term like PSC, TSC, that are the pressure and temperature, the surface conditions, flow rate of the gas, that is QG, and the log dependence of the terms like K, T, viscosity and compressibility as well. So this is the final exact solution of the diffusivity equation for real gases. So for the numerical purpose, there are other forms of the equation as well that is obtained, that are equation number 13 can be obtained by placing PSC and TSC as 14.7 psi and 520 Rankine. These are the other two forms, equation number 14 and 15. And equation number 14 you can see that there is a term called TD, that is dimensionless time. There is a term called gamma, that is Euler constant, and also in the equation number 15 there is a term called pseudo pressure drop. So these are the different forms of equation, but mainly we have to remember the equation number 12. So let us move on the other two methods. Just we will see the results of these two methods. We will not derive it as we have done in the MP method. So you can see that the difference is there are squared terms of PWF and PI that are obtained by using the concept of average pressure. So you can see that there are the terms called mu bar and Z bar, that are the viscosity and compressibility at the average pressure. And the limitation of this method is we can use it when the reservoir pressure is less than 2000, and at many times we will consider that the average conditions are equal to initial conditions, which is not so for all the cases. So that is the limitation of this method. And the third method is the pressure method, that is pressure approximation method. In this method the basic concept is by using the pseudo liquid term. We will consider that the gas is behaving like a liquid. So we will incorporate another factor, that is of the formation volume factor, used to solve this equation. And there is a pressure dependence of PWF and PI on BG. And another concept that we require is that these equations can be applied only when at the higher pressures. That was suggested. So now let us see the comparison of all the three methods. As you can see that in the graph 1, P by mu z is a linear function of the pressure. So that is the only the linearity can be obtained, or equality can be set up between the two of the methods as MP bar minus MPWF that we have initially derived. That is the real gas potential terms will be equal to this P square by PWF square. So you can see that how the square terms are related to the gas potentials. So area under that curve will give you the integration from PWF to P bar, P del P by mu z. This is the theoretical idea. In the graph 2 you can see that the linearity can be only obtained at the higher pressures and the lower pressures. So in between there is a small area which is not behaving linearly. So why is it so? So two different solution techniques are liable to give different results in between this area. Approximately same answers will be obtained, and another thing is that when the drawdown will be high, the different results will be obtained. Otherwise the same result will be obtained in between the plot. For further explanation you can go through the fundamentals of reservoir engineering, that is from L.P. Dake and Tarek Ahmed. I have taken this content from there, so you can go through it for the further simplification and understanding. So this is the final conclusion that we can made, that why we have adopted that gas pseudo pressure terms. Why? Because we were not concerned about the pressure ranges. P square method helps in using that equation in any ranges of the pressure that we have seen, that less than 2000, greater than 3000. So one does not have to concerned about that. Now MP method is technically more simple method to use, and it is the used worldwide more in more proportion. So the necessity of iteration in solving the inflow equation for PWF is avoided. So easily the solutions are obtained, and there are always the limitations and advantages of everything. So these are some of the 4 points that I have tried to explain, and this technique is widely used in current literature. So MP method, why we have used MP method is it is used worldwide. So thank you. I hope you liked the presentation. Thank you so much.